So when it comes to integration, before we talk about the theory, the techniques and application of integrals, let's just try to answer a very simple question. And that is, how do I find the area under a curve? Now, of course, there are many different types of curves, and there are a lot of special cases that we can have, but we're going to specifically look at the case where we have a function that is positive, is continuous over an interval that's closed, so my question is, how can I calculate this area? Of course, we have very nice special cases. If the function is a constant function, say from 1 to 5, and it is say 4, then the area would be 4 times 5 minus 1, which is 16 units square. If, for example, your function is a quarter circle, say y equal to square root of 4 minus x squared, where x is between 0 and 2, then the area under the curve would be quarter of pi r square, which is pi. And those are all nice. And we can use geometry in calculating those. There are some homework problems that you may see later like that. But now let's answer the question, the original question. How do I calculate the area under this eyebrow curve? Well, if you're allowing rough estimates, you can always say, well, that area would be approximately equal to area of that rectangle. So if this is A to B, the height of the rectangle is f of A. So the area would be approximately f of A times B minus A. If you don't like that estimate, maybe you can use the other endpoint as your height. Another rough estimate, but area would be f of B times B minus A. Both are not very good estimates, but they are estimates of this function. Now, I can notice that when I use the first one, I'm actually using the value at A, as my height, and A is a left endpoint for the interval. For the second one, I use the value of B, and B is the right endpoint. For the interval. So roughly speaking, one is a left endpoint calculation, one is a right endpoint calculation, both approximations of the area. To improve the approximation, I can divide, let me just draw it on a nice clean picture. I can divide my interval into two pieces. And for ease, I'm going to make sure that the two pieces have the same width. We refer to this later on as a regular partition. The regular part means the size of each partition, the width of each partition part is the same. For this one now, if I use, say, the left endpoint calculation, I would get a height at A and a height at this value, which I'm going to tell you. This would be A plus B minus A over 2. You could say it's A plus B over 2, but for building some uniformity, I'm just going to call it A plus B minus A over 2. Then for this one, the left endpoint calculation with the two a partition size 2, L2, is f of a times b minus a over 2. That b minus a over 2 is the width of the rectangle, plus f of a plus b minus a over 2 times b minus a over 2. Again, that is the width of the rectangle. If on the other hand, if I was going to do the right endpoint, then it would be this guy and this guy. So R2 would be f of a plus b minus a over 2 times b minus a over 2 plus f of b times b minus a over 2. As you can see, it can be very tedious if I each time want to say b minus a over 2, and the factor here would be a little bit hard to write each time. You can continue this to add to your precision in hope that at some point it would approach a limiting value, and that value would be the area that you're looking for. Before I get into more detailed calculations of the process, let me give you guys a concrete example. Suppose I'm talking about a function f of x equal to x squared over interval 1 to 5, and let's say n is equal to 4. Now, disregarding the scale here, if I just draw this, this is the area I'm trying to calculate. Now, if I do the left endpoint calculation, I'm calculating the area of each by looking at the height at the left endpoint, the area of each by the height at the left endpoint, the area of the height at the left endpoint. The area of this rectangle would be the height at the left endpoint. So L4, using a partition size 4, is f of 1 times 1, and the second one is the length of the width of each rectangle. F of 2 times 1 again, f of 3 times 1, and f of 4 times 1. Which I can simply write it as f of 1, f of 2, f of 3, f of 4 times 1. Being a squaring function is going to be 1 square, 2 square, 3 square, 4 square times 1. 1 plus 4 plus 9 plus 16 times 1, which is 30. On the other hand, if I use right endpoint calculation for the very first rectangle, the right endpoint value height would be this, and that would be my rectangle. The right endpoint value would be this. That would be my rectangle. That would be my rectangle if I use a right endpoint, and this would be my right endpoint calculation for that rectangle. So for R4, I get f of 2 plus f of 3 plus f of 4 plus f of 5, once again times 1 as the width of the rectangle. Is 2 square plus 3 square plus 4 square plus 5 square times 1. 4 plus 9 plus 16 plus 25. Which is going to be 54. Again, unit square and unit square, whatever the area is. Neither of them are, of course, the value of the area. In fact, the averaging process doesn't work here because I don't have straight lines. These are all curves. in exaggerated form there. If it was straight, I would say the area of top and bottom are the same, so I can just average out. But since it's a curve, there is more that's going to be over X approximation than the under approximation. So it is not an averaging process that I can do there. Okay. How do I improve this approximation? I can just keep adding to the partitions. Go from 4 to 8 to 16 to 32 to 64 and such. There's no need to approximate to increase the partitions by doubling it. It just makes very nice calculations and nice numbers. But you can just go like one each time, add one more partition. It's just harder to graph and harder to visualize. So the area would be limit as n goes to infinity of either right endpoint or left endpoint if the limits are exist, would be the same value. And that would be the area. We have a notation for that, which we're going to introduce later. Right now, we're just trying to calculate the areas. We're just trying to calculate the area. Okay. So to make our writing a little bit easier and to make it a little bit simpler when we're writing things like this, or to calculating what we had b minus a over 2 or b minus a over 3 or 4 or whatever, let's go ahead and introduce some notation. First, I hope you all agree that if my interval is from a to b, and I cut it into n pieces, the width of each piece would be b minus a over n. I hope you're agree on that. The width of each of those will be b minus a over n. Now, that is your delta x. And if this is a, this will be a plus delta x. This will be a plus 2 delta x. This will be a plus 3 delta x. This will be a plus 4 delta x. A plus n minus 1 delta x. And finally, a plus n delta x, which is b. So that's what each of those endpoints would be. For left approximation, for n partitions, would be sum I equal to 0 to n minus 1, f of a plus I delta x. That's the left endpoints for each interval, and this is the width of each interval. On the other hand, right endpoint would be I equal to 1 to n of f of a plus I delta x. Just to quickly visualize what's happening. When I is 0 on the first one, when I is equal to 0, then you have 0 delta x, which is 0. So you just get a from the whole thing, and that's the first endpoint, first left endpoint. When I is 1, you get a plus 1 delta x, that's the second endpoint, second left endpoint. And then similarly, third left endpoint. At the final value of n minus 1, you get the a plus n minus 1 delta x, which is the last left endpoint. Similar here, when I is 1, you get a plus a delta x, which is here, a plus 2 delta x, 3 delta x, 4 delta x, and finally n delta x, which is n times b minus a over n, which is just b minus a. And if you add a to b minus a, you just get b. So that's how you end up there. So it covers all the intervals, the whole partition. And one of them only looks at the left endpoints for each interval, which misses the very last endpoint. And one of them looks at the first endpoint for each interval, right endpoint for each interval, which misses the first endpoint. Because A is not a right endpoint and B is not a left endpoint. That's the summary, that's a notation for this. Okay. This is called Riemann sum. This is called Riemann sum. And of course, if I take the limit of that, limit of the Riemann sum is the area, and we have a name for that. I'm going to, again, formally define both of those. Okay. So that's the idea so far of both what are we trying to do and a notation to make our process a little bit easier. Now, let's do a concrete example in which we are going to, in fact, evaluate the area under the curve using the whole limit of the Riemann sum. And then I formally define what these represent. Let's say that, again, I go with the x squared problem. Find the exact value for the area under the curve y equal to x squared, or f of x equal to x squared, between or over 1 to 5. So I just stay with the same problem. For this problem, I guess for ease of notation, I'm going to use right endpoint, but you can do left endpoint as well, similar. So the area is limit as n goes to infinity of Rn, which is limit as n goes to infinity of sum I equal to 1 to n f of a plus I delta x. Now let's go ahead and fill in the things we know. F is x squared, is squaring function, but we're going to get to that later. A is 1. Delta x is b minus a over n. B is 5, a is 1, and of course, so it's going to be 4 over n. That was something I stated earlier, and I think that was able to justify that well. Now, I can go further with this, but know this before I write any more. 4 over n does not depend on the summation, so that can be pulled out of the summation. Just a nice exercise of the summation process. F is squaring function. And then I'm just going to expand the square part. I get 1 plus 8i over n plus 16i squared over n squared. I'm going to split the sums into 3 sums. Again, attempting calculating each of the sums. Sum of 1 to n of 1 is just n, because adding 1 to itself n times is just n. I can pull out the 8 over n from the second summation because it is not dependent on I. The only things that depend on I would be affected by the summation. So I and I squared remain inside the summation. Once again, 4 over n, I keep it out for now. Sum of I, adding all the numbers from 1 to n. If you guys remember, there's a formula from that from your algebra or pre-calculus class, depending which you took. That's going to be n plus 1 over 2. And sum of the squares of the numbers from 1 to n would be n plus 1, 2n plus 1 over 6. Those two formulas again come from your algebra or pre-calculus classes you may have taken in the past. If not, just know that this summation amounts to this, and this summation amounts to this. Taking a common denominator. Again, now this is all just algebra before I have to calculate the limit. Combine the square terms, n terms, and the constant term. Now, extra work here, but dividing top and bottom by n squared. If you remember, that's one thing we did when we had fractions and taking the limit of the variable as going to infinity, as the variable goes to infinity. These two go to 0 as n goes to infinity. So, and then the last part is just constant with respect to, so you get 124 over 3. The limit exists, and the limit is the area. So the area of this piece, the exact area of this piece is 124/3. So let me fill in the blank here now. If the area exists, the limits exist, that would be the area, and the notation for it is, we use elongated S for the integral sign, and that's area or integral from A to B. That's the bounds of your interval, the function, and the variable that you integrate with respect. So this is corresponds to your delta x. This corresponds to your function. And this is the left bound of your interval. This is the right bound of your interval. Switching any of those would change things. This summation that I wrote here is called Riemann sum. Now, normally for Riemann sum, we have a more general form of writing it. We write it as sum I equal to 1 to n of f of xi star delta x. Xi star is supposed to be any, if this is the ith interval, any value in between could be xi star. It could be the left endpoint, it could be the right endpoint, it could be anything. anything that falls in that interval. So this is a general form of a Riemann sum. If I put a limit before it, then this becomes limit of a Riemann sum. And if the limit exists, that becomes the integral form. And this is called Riemann integral. Okay. Now for practice, find the area under the curve f of x equal to 1/2 x cubed over the interval 0, 1. Use limit of the Riemann sum with right endpoint approximation. That'd be a good thing to practice or calculate by the next video. Thank you.